Hello there. Welcome to the Science Owl Station. Today, we begin a quiet journey, not across lands or seas, but across the deepest, most profound expanse there is. Tonight, we gently untether from the familiar pull of our world and drift into the silent, star-dusted ocean of the cosmos itself. We are going to explore the universe. That single word holds within it everything that ever was, everything that is, and everything that will be. So, wherever you are right now, perhaps tucked under a blanket or resting your head on a pillow, I invite you to let your gaze soften. Take a slow, deep breath and feel the small, steady rhythm of your own being. As you do, imagine that rhythm joining a far grander, slower, more ancient beat, the heartbeat of the cosmos. Before we speak of its age, its size, or its mysteries, let us first ask the most fundamental question. What is the universe? In its simplest, most awe-inspiring definition, the universe is the totality of all space and time, all matter and energy. It is not merely a container holding galaxies. It is the galaxies, the void between them, the very fabric in which they are woven. It is the history of existence, from the first fleeting moment to the distant, uncertain future. Think of it as the ultimate story, and every particle, every beam of light, every swirling nebula is a word in its infinite narrative. Right now, as you listen, you are within this story. The air you breathe, composed of ancient atoms forged in stellar hearts, is part of the universe. The device through which you hear this voice, a product of human curiosity, is part of the universe observing itself. From the subatomic realm, where quantum particles flicker in and out of existence in a probabilistic dance, to the vast architectural scales of superclusters of galaxies, it is all one interconnected reality. There is no outside. When we look up at the night sky, we are not looking out at something separate from us. We are looking deeper into our own cosmic home. This home is built upon relationships. The matter that forms your hand is held together by forces. The strong nuclear force binding atomic nuclei, the electromagnetic force orchestrating chemistry, the gentle, persistent tug of gravity. These forces are not human inventions. They are the universal rules of engagement, written into the fabric of reality during its earliest moments. They govern the spin of electrons and the orbit of planets with the same fundamental principles. This elegant consistency is what allows us to understand distant stars by studying the physics in our laboratories. It suggests a profound unity, a cosmic harmony underlying the apparent chaos. So, as we begin, I want you to hold this feeling of being both profoundly small and profoundly connected. You are a tiny, conscious speck on a pale blue dot orbiting an average star in the suburbs of a spiral galaxy. And yet, you are made of star stuff, a collection of atoms that have journeyed for billions of years across the void to come together, for a cosmic instant, into a form that can wonder about its own origins. That wonder is our starting point. As we explore, we will not rush. We will linger on ideas, float through concepts, and let the scale of it all wash over us like a slow, tidal wave of quiet amazement. Wherever you are, let the world slow down for a while. Soften your gaze, let the hum of life around you fade, and gently drift with us into tonight's quiet exploration. The story of our understanding of the cosmos is a story of expanding horizons. For millennia, our universe was what we could see with our eyes. The dome of the sky, the points of light traversing it. Our ancestors told stories, mapping the heavens with constellations that reflected their lives and myths. Then came the telescope and our world exploded. The points of light became other worlds, other suns. Our Milky Way galaxy became an island of stars, and for a time we thought it might be the entirety of creation. But in the early 20th century, a profound realization dawned. Those faint, fuzzy nebulae were not clouds within our galaxy. They were galaxies in their own right, unimaginably distant islands of light. Suddenly, the universe became a place of galaxies, a vast archipelago in an ocean of darkness. This was the first great expansion of our cosmic perspective, not a physical expansion, but an expansion of the mind. We realized our home was not the center, but a single thread in a much grander tapestry. This shift from a single galaxy to a universe of galaxies is the foundation of modern cosmology. It taught us humility and ignited a deeper curiosity. It set the stage for the next, even more startling discovery: that this grand tapestry itself is not static, but dynamically, relentlessly growing. Let us sit with that idea for a moment, a growing tapestry and expanding reality. To truly appreciate it, we must attempt to grasp its scale, a task that is ultimately humbling and gently bewildering. Our minds evolved to navigate forests and savannas, to judge the distance to a water source or the height of a tree. The scales of the cosmos defy our innate intuition. They are numbers that feel more like philosophy than measurement. Yet, if we approach them not with a need to fully comprehend, but with a sense of reverent awe, we can feel their resonance. So, let your mind stretch slowly, like waking from a deep sleep, and picture this. Our universe has an age. It is not infinitely old. Based on the relentless expansion we observe and the echo of its birth we can detect, scientists have calculated that the universe, as we know it, began its story approximately 13.8 billion years ago. Say that number softly to yourself. 13.8 billion years. It is a span of time so vast that every human history, every mountain range's rise and fall, every lifetime of every creature that has ever walked the earth is but a fleeting whisper within it. This is the cosmic timeline, and our present moment is its very leading edge. Now, consider the size that corresponds to this age. Because the universe has been expanding for all that time, the space we can see, the observable universe, is not 13.8 billion light-years across. Light from the most distant objects has had much longer to travel as space itself has stretched beneath its journey. The result is a sphere centered on us, with a radius of about 46.5 billion light-years. That means the diameter of our observable cosmos is roughly 93 billion light-years. Picture a sphere of such stupefying proportions. A single light-year is the distance light, the fastest thing in the universe, travels in 1 year, about 9.46 trillion kilometers. Multiply that by 93 billion. The numbers become abstract, mere poetry. But the meaning is clear. The stage is almost inconceivably large. Within this observable sphere lie perhaps 2 trillion galaxies. Each galaxy, like our own Milky Way, is a gravitationally bound island of hundreds of billions of stars. Each star may host a family of planets. The sheer abundance is a form of cosmic comfort. We are not in a sparse, lonely void, but in a teeming metropolis of matter and light. Most of it so distant its combined light appears to us as a faint cosmic glow. And here lies a crucial, soothing thought. The universe we can see, the 2 trillion galaxies, the brilliant quasars, the swirling nebulae, is, by definition, just our local view. It is the portion of the greater whole from which light has had time, since the beginning, to reach our tiny vantage point. What lies beyond this cosmic horizon? The full, true universe may well be infinite. There may be no beyond, in the sense that space simply continues forever, with more galaxies, more stars, more possibilities stretching into endlessness. The observable universe is our shared cosmic neighborhood. The rest is a quiet, eternal mystery. This scale changes our perception of time as well. When we look at a distant galaxy, we are not seeing it as it is now, but as it was then, when the light left it on its long journey to our telescopes. Gaze at a galaxy 100 million light-years away, and you are witnessing a world from the time of the dinosaurs on Earth. Look at the light from a galaxy near the observable horizon, and you are seeing infant galaxies as they appeared just a few 100 million years after the Big Bang. Astronomy is the only science that is also a form of time travel. Every glance upward is a look into the deep past. This means the night sky is not a static painting, but a layered historical archive. The faintest, most redshifted smudges of light are cosmic infancy portraits. The brilliant disk of Andromeda is a snapshot from 2.5 million years ago. Even sunlight is 8 minutes old by the time it touches your skin. We are forever surrounded by ghosts of cosmic events, their stories arriving piecemeal, delayed by the vast, silent distances between the stars. So, as you rest there, feel the immensity not as a source of anxiety, but as a profound, deep space in which to relax. Your concerns, your to-do lists, the minute-by-minute pulse of daily life, all of it exists on a tiny, fragile, beautiful world suspended in this ocean of expanding space-time. The scale does not diminish us. Instead, it frames our existence with a breathtaking context. We are latecomers to a story that began 13.8 billion years ago, living in a small corner of a stage 93 billion light-years across, surrounded by the gentle, ancient light of countless other worlds. It is a perspective that invites a long, slow exhale. There is time here. There is space here. All is unfolding as it should, at the majestic, patient pace of cosmology itself. And within this grand structure, matter is not scattered randomly. It has gathered, clustered, and woven itself into a pattern of breathtaking order. A cosmic web that connects everything, from the greatest galaxy cluster to the atom in your resting body. If the scale of the universe invites a slow exhale, its architecture invites a wondering gaze. For the cosmos is not a formless cloud of scattered stars. Out of the primordial simplicity of the early universe, matter has gathered itself over billions of years into a structure of such delicate, intricate grandeur that it resembles a vast, three-dimensional spider's web, spun on scales that dwarf human imagination. This is the cosmic web, the large-scale structure of the universe, and it is the home in which our galaxy resides. Picture it not with the sharp, clinical lines of a diagram, but as a soft, luminous tapestry woven into the dark velvet of space, its threads glowing with the collective light of a billion suns. At the heart of this structure are two complementary realities: the dense, bright filaments and the immense, dark voids. Let's first drift through the filaments. These are the rivers and highways of the cosmos, great twisting tendrils of dark matter and intergalactic gas, along which galaxies are strung like pearls on a necklace. They can stretch for hundreds of millions of light years, connecting massive nodes where several filaments intersect. These intersections are the densest regions in the universe, the great clusters and superclusters of galaxies. Here, thousands of galaxies swarm in a relatively small volume of space, bound together in a gravitational dance so complex and slow it makes the waltz of planets seem like a frantic twirl. Our own Milky Way is part of such a structure. We belong to a small group of galaxies called, simply, the local group, which is itself a minor filamentary spur on the outskirts of a much larger supercluster named Laniakea, a Hawaiian word meaning immense heaven. Laniakea is a vast, flowing continent of galaxies, all gently streaming toward a common center of gravity known as the Great Attractor, a hidden gravitational focal point behind the dust of our own galactic plane. Now, let your mind float away from these dense, brilliant rivers and into the spaces between them. These are the cosmic voids. If filaments are the continents, voids are the oceans, vast, nearly empty expanses that can be 100 million light years or more across. They are not completely empty. They contain a few isolated field galaxies and a wispy haze of hydrogen gas. But their density is so low, their darkness so profound, that if our galaxy were placed in the heart of a void, our night sky would be almost black, with only the faintest, loneliest pinpricks of light from our nearest neighbors. These voids are the counterpoint to the filaments, the negative space that gives the positive structure its form. The universe, in its total structure, is a froth of bubbles, where the walls of the bubbles are the luminous filaments, and the interiors are these immense, quiet hollows. It is a pattern that emerged from tiny, random quantum fluctuations in the first instance after the Big Bang, amplified over cosmic time by the relentless, patient pull of gravity. This brings us to the gentle, unseen hand that sculpted this web, gravity. It is the universe's great artist, working on a canvas of space-time with a brushstroke that spans eons. In the early, nearly smooth soup of matter and radiation, slightly denser regions had just a little more gravitational pull. They began to attract more matter from their surroundings. Over hundreds of millions of years, these regions grew, drawing in gas and dark matter, slowly emptying the areas around them, creating the seeds of voids. The material flowed along lines of gravitational attraction, forming the great filaments and pooled at their intersections. It is a process as natural and inevitable as water finding the lowest path in a landscape. Only here, the landscape is the fabric of space itself, and the water is all the visible and invisible stuff of creation. This growth is slow and graceful. A supercluster takes billions of years to assemble itself. We are witnessing this architecture not as a finished, static monument, but as a living, evolving sculpture, still being shaped by the same gentle, universal force that holds you in your chair and guides the moon around the earth. As you rest, consider your place within this web. You are on a planet orbiting a star in a galaxy that is one of hundreds of billions in the Milky Way. Our galaxy is moving at a serene pace of several hundred kilometers per second along its filamentary path within the Laniakea supercluster toward the unseen pull of the Great Attractor. It is a journey that began long before Earth formed and will continue long after our star grows cold. There is a profound tranquility in this motion. It is not a frantic rush, but a cosmic drift, a gentle sailing on the grandest of tides. We are not at the center of this web, nor in a specially dense or sparse region. We are, it seems, in an ordinary neighborhood of an ordinary filament in an ordinary supercluster, and there is a deep, soothing beauty in that ordinariness. It tells us that the laws of physics that crafted our home are the same everywhere. The same gentle gravity, the same patient processes have woven similar tapestries of light and void across the entire observable universe, and likely beyond. We are not in a special place, but we are in a place that is connected to everything else by invisible threads of force and a shared history written in the slow, sure language of gravitational collapse and expansion. This connected, structured cosmos is the stage upon which the next great act of our story unfolds. The discovery that this entire stage is itself growing, stretching, and evolving in a way that forever changed our understanding of the universe's destiny. In the quiet cathedral of the cosmic web, with its grand filaments and silent voids, there is a subtle, pervasive motion that underlies everything. It is not the gentle orbital dances within galaxies, nor the slow drift of galaxies along their filamentary rivers. This motion is far more fundamental. It is the very stretching of the stage upon which all these dances are performed. The universe is not static. It is expanding. This realization, one of the most profound in human thought, transforms the cosmos from a grand, permanent sculpture into a living, breathing entity, slowly unfurling in the silent dark. Let us explore this gentle, relentless expansion, a concept that soothes as much as it astounds, for it speaks of a universe with a history, a beginning, and a destiny. The story of this discovery begins not in the vastness of space, but in the careful, patient work of astronomers in the early 20th century. Scientists like Vesto Slipher and later Edwin Hubble were studying the light from distant spiral nebulae, what we now know to be other galaxies. By splitting their light into spectra, rainbows that reveal the chemical fingerprints of elements, they noticed something peculiar. The familiar patterns of lines, signatures of hydrogen, helium, and calcium were not precisely where they should be. They were shifted toward the red end of the spectrum. This redshift is a cosmic version of the Doppler effect, the same phenomenon that causes the pitch of a siren to drop as an ambulance speeds away from you. But here it was light waves being stretched, their wavelength lengthened. The inescapable conclusion was that these galaxies were moving away from us, and the farther away a galaxy was, the greater its redshift, and thus the faster it appeared to be receding. This is Hubble's law, a beautifully simple yet deeply revolutionary principle. The velocity of a galaxy's recession is proportional to its distance from us. A galaxy twice as far away is moving away twice as fast. It is crucial to feel what this means. It does not mean we are at the center of some cosmic explosion, with everyone fleeing from us specifically. Imagine, instead, a loaf of raisin bread rising in the oven. As the dough expands uniformly, every raisin moves away from every other raisin. From the perspective of any single raisin, all the others are receding, and the farther away a raisin is, the faster the expanding dough carries it away. We are simply one raisin among countless others, experiencing the same universal expansion. Every galaxy group, every observer anywhere in the cosmos would see the same view, all other galaxies speeding away, their speeds dictated by distance. What is expanding, then? It is space itself. The fabric of space-time, the ultimate container of all things, is being stretched. The galaxies are not for the most part, plowing through a pre-existing static space like ships on a sea. They are more like buoys resting on the surface of an ocean that is itself growing wider. The space between the buoys increases, but the buoys themselves remain relatively anchored in their local patch of water. This is why, within our local group of galaxies, gravity has triumphed over this expansion. The Milky Way and Andromeda are actually moving toward each other, destined to merge in billions of years, because their gravitational bond is strong enough to overcome the gentle background stretching of the space between them. Expansion dominates on the vast, intergalactic scales where gravity's grip is weaker, in the great distances between galaxy clusters and along the spans of the cosmic web's empty voids. This leads us to a single elegant parameter that describes the tempo of this cosmic expansion: the Hubble constant. It is the rate at which the universe is expanding today. Current measurements suggest that for every megaparsec, a distance of about 3.26 million light-years, a galaxy is from us, it appears to recede about 70 kilometers per second faster. Contemplate that pace. It is serene, almost lazy on human scales. Over 1 million years, a galaxy 1 megaparsec away will have moved only a tiny fraction further due to this expansion. But compounded over billions of years, across billions of light years, this gentle, unceasing stretch has created the vast distances we see today. It is the reason the night sky is dark, because the stretching of space has redshifted the light from the earliest, most prolific stars into invisible infrared waves, preventing the sky from being a searing, continuous wall of light. The expansion has given us a dark, quiet canvas upon which the pinpricks of nearby stars and galaxies can softly shine. As you breathe in and out, consider that the very space around you is part of this expansion. The space between atoms in your body, the space between the Earth and the Sun, is held rigidly together by electromagnetic and gravitational forces far stronger than the background expansion. So you are not stretching. Your room is not growing. But on the largest scales, where no forces bind structures together, the universe is steadily, patiently growing more spacious. It is a cooling thought. The cosmos is not claustrophobic or static. It is opening up, creating more room, more potential, more future. This expansion is also our ultimate time machine. Because light takes time to travel and space has stretched during its journey, the redshift of a galaxy tells us both its distance and, by rewinding the expansion, its age. It allows us to map not just where things are, but when they were. The expansion of the universe is the thread that ties its size to its age, weaving together the concepts of space and time into a single, unfolding narrative. And as we will see, this narrative took an even more mysterious turn at the end of the 20th century, when we discovered that this expansion is not just continuing, but accelerating. A discovery that points to a hidden, dominant force woven into the empty spaces between the web's threads. An energy of the vacuum, a gentle push in the dark. So, we have a universe that is expanding, a vast and intricate web of luminous matter stretching across the growing darkness. But as astronomers mapped the motions within this web, a profound puzzle emerged. A whisper of something missing, a gravitational signature that did not match the visible script. The stars at the outer edges of spiral galaxies were whirling around the galactic center far too quickly. Entire clusters of galaxies were moving with a collective gravity that the sum of all their shining stars, gas, and dust could not possibly produce. It was as if the visible universe was merely the embroidery on a much larger, darker fabric. As if every galaxy, every cluster, was embedded in a massive, invisible halo of something. This something, which neither emits, absorbs, nor reflects light, we call dark matter. It is the universe's silent partner, its unseen architecture, and it constitutes not a small fraction, but the overwhelming majority, about 27%, of all the matter and energy content of the cosmos. Let us gently unpack what this means. For most of human history, we have equated reality with what we can see. But dark matter teaches us that our eyes, and even our most powerful telescopes, are tuned to only a tiny sliver of what is actually there. Dark matter is not black holes or dark clouds of ordinary gas. It is something fundamentally different. Based on its gravitational effects, we know it must be a form of matter. It has mass and responds to gravity. But it seems to interact with light and with ordinary matter, the stuff of stars and planets and us, only through that gravitational pull. It is, for all other intents and purposes, transparent and intangible. It does not clump into stars or planets. It forms vast, diffuse halos that envelop galaxies and permeate the spaces between them, and it weaves the underlying scaffold upon which the luminous cosmic web is hung. We can think of it like this. Imagine you are watching a majestic, swirling dance of glitter in a sunbeam. The glitter is beautiful, tracing elegant arcs and patterns. But what you cannot see is the calm, deep river current in which the glitter is suspended, a current that guides its motion and shapes its flow. The glitter is the visible baryonic matter, the stars and galaxies. The deep, invisible current is the dark matter. We do not see the current itself, but we infer its presence, its strength, and its shape entirely from the motion of the glitter. This is how we know dark matter is there. We see its ghostly gravitational hand holding fast-spinning galaxies together, preventing them from flying apart. We see its immense gravitational lens bending the light from distant galaxies behind it, creating distorted, magnified arcs and rings, a phenomenon called gravitational lensing, where the dark matter acts as a cosmic magnifying glass made of sheer gravity. What could it be made of? This is one of the great open questions. The leading idea is that it consists of as yet undiscovered elementary particles, slow-moving and massive, that emerged from the hot dawn of the universe. Scientists have given these hypothetical particles names like WIMPs, weakly interacting massive particles. They would be everywhere, a cosmic sea through which we move without noticing, billions of them passing through your body every second without a single interaction. Other theories propose different candidates, like axions, or even suggest subtle modifications to our understanding of gravity itself. But the gravitational evidence is so robust that most cosmologists agree. Most of the matter in the universe is dark, hidden, and of a nature fundamentally alien to our everyday experience. This realization is strangely humbling and expansive. We are not just made of the rare, luminous stuff. We and everything we see are the minor exception, the froth on the surface of a deep, dark ocean, the beautiful spiral of Andromeda, the grand sweep of the Milky Way across the night sky, are just the visible tracer lights outlining a form that is vaster, heavier, and invisible. There is a profound lesson here about the limits of our senses and the power of our curiosity. Through reason, mathematics, and careful observation, we have been able to see an entity that is completely invisible, to map its distribution across billions of light years, and to understand that it is the primary gravitational glue holding the cosmic structures together. It is a testament to the fact that the universe is knowable, even in its most hidden aspects. As you rest in the quiet, consider the gentle, pervasive presence of this unseen world. The chair that supports you, the floor beneath it, is held firm by gravity, a force that is, right now, being shaped not just by the earth beneath you, but by the vast, diffuse halo of dark matter in which our entire galaxy is embedded. You are living and breathing within a transparency, a universe filled with ghostly mass. It does not threaten or obscure, it supports and shapes. It is the hidden framework that allowed galaxies to form early enough for stars like our sun to be born, for planets to coalesce, and for the long chain of events leading to this moment of quiet contemplation to unfold. And as we will see, this mysterious dark matter is only one part of the cosmic unknown. For when we add up all the matter, dark and luminous, we account for only about 32% of the universe's total content. The remaining 68%, an even more enigmatic force, is what drives the cosmic expansion itself to not just continue, but to accelerate. This is the realm of dark energy, the gentle, persistent push in the void. We have met the universe's silent partner, the invisible mass that sculpts the cosmos. But as we peer deeper into the unfolding story, we encounter a presence even more pervasive, more subtle, and fundamentally more mysterious. It is not matter at all, but a property of space itself, a gentle, relentless pressure embedded in the vacuum. This is dark energy, and it is the dominant component of our universe, constituting roughly 68% of its total energy budget. If dark matter is the unseen scaffold, dark energy is the silent breath steadily inflating the entire structure, causing the expansion of the universe not merely to continue, but to accelerate. This discovery, made just over 2 decades ago, reshaped our cosmic narrative and unveiled a profound enigma lying at the heart of empty space. To understand this gentle acceleration, let us rewind to a fundamental expectation. After the colossal impulse of the Big Bang, everything was rushing apart. Gravity, the universal force of attraction, acts on all this matter, both luminous and dark, pulling it together. Imagine throwing a ball straight up into the air. You expect gravity to slow its ascent, eventually bringing it to a momentary stop before it falls back down. For most of the 20th century, cosmologists believed the universe was doing just that, expanding but gradually slowing down under the collective gravity of all its matter. The great question was whether there was enough matter to eventually halt the expansion and pull everything back in a big crunch, or whether the expansion would simply coast onward forever, slowing to a near standstill. Then, in the late 1990s, 2 independent teams of astronomers were studying distant stellar explosions called Type Ia supernovae. These supernovae are cosmic standard candles. Their intrinsic brightness is known, so by measuring how dim they appear, we can gauge their distance with precision. Simultaneously, by measuring their redshift, we know how much the universe has stretched since their light was emitted. What these teams found was startling. The most distant, ancient supernovae were fainter than they should have been if the universe had been coasting or slowing down. The only explanation was that, in the past, the universe was expanding more slowly than it is today. The expansion is speeding up. It was as if that ball thrown upward, against all expectation, began to soar away faster and faster, as if gravity's pull were being overcome by some hidden repulsive force. This force is what we call dark energy. What could it be? The leading and simplest explanation is something Albert Einstein himself considered and later discarded: the cosmological constant. In Einstein's equations of general relativity, there is a term, denoted by the Greek letter lambda, that represents a constant energy density inherent to the fabric of space itself. Think of empty space not as a true void, but as a quantum foam, seething with transient particles that flicker in and out of existence. This quantum activity endows every cubic centimeter of vacuum with a tiny, constant energy. On human scales, this energy is immeasurably small and utterly insignificant. But across the vast, nearly empty volumes between galaxies and within cosmic voids, this tiny energy adds up. And because it is a property of space itself, as the universe expands and more space is created, more of this dark energy comes into being. Its repulsive gravitational effect, yes, in general relativity, a constant positive energy density creates a kind of gravitational repulsion, becomes dominant, pushing galaxies apart ever faster. The implications are profound and strangely serene. Dark energy dictates the long-term fate of the cosmos. In a universe dominated by this gentle repulsion, the expansion will continue to accelerate. Galaxies not already bound together by gravity will see the space between them stretch at an ever-increasing rate. Billions of years from now, a hypothetical observer in our Milky Way, long merged with Andromeda, would look out into a profoundly darkened sky. All other galaxy clusters will have been swept beyond a cosmic horizon, their light redshifted into oblivion, their existence erased from our observable universe. The cosmos will become a vast, expanding isolation of island galaxy clusters adrift in an ever-cooling, ever-quieting void. A fate cosmologists call the Big Freeze or heat death. It is not a violent end, but a slow, deep fading into maximum entropy, a state of equilibrium where all energy is evenly distributed and no more work can be done. As you rest here in the present, consider the quiet ubiquity of this force. The space in your room, between the words of this sentence, is imbued with this faint, repulsive energy. It is not something you can feel. Its effect is quadrillions of times weaker than the gravity holding you to Earth. But on the grandest scales, it is the conductor of the cosmic symphony, setting the tempo for the universe's unfolding. Its discovery reminds us that the vacuum is not empty. Empty space is a rich, dynamic entity, the foundational stage upon which the drama of matter plays out. The interplay between dark matter and dark energy is the great cosmic tug-of-war that has shaped our epoch. In the early, dense universe, dark matter's gravity dominated, pulling matter together to form galaxies and clusters. But as the universe expanded and thinned out, the constant density of dark energy eventually came to dominate over the diluting matter. We live in a special transitional time, roughly 13.8 billion years after the beginning, where both forces are dynamically significant and we are observant enough to detect them. There is a peaceful poetry in this balance. The inward pull of the unseen dark matter once gathered the galaxies, and now the outward push of the empty, dark energy is setting them adrift. We exist in the moment between the gathering and the dispersal, in the sweet spot where the cosmos is structured, luminous, and knowable. So, as we let the concept of dark energy settle in our minds, we can view it not as a threat, but as the deep, steady rhythm of space-time itself. It is the universe breathing out, in a long, slow exhalation that began infinitesimally and will continue for trillions of years. And in this vast composition dominated by dark, unseen elements, we must now turn our attention to the small, shining fraction that makes up our tangible reality, the mere 5% of the universe that is ordinary atomic matter. This is the stuff of stars, planets, and life. The luminous tracer in the dark, the precious, complex result of cosmic evolution. After contemplating the vast, unseen dominions of dark matter and dark energy, there is a certain comfort in returning our gaze to the familiar, to the tangible, to the world of light and substance that our senses perceive and our sciences have long studied. This is the realm of ordinary matter, sometimes called baryonic matter. It is everything you can see, touch, and are made of. The stars that ignite the night, the planets that circle them, the rocks, the oceans, the air in your lungs, and the very atoms that orchestrate the dance of life. Yet, for all its centrality to our experience, it is the cosmic minority. Ordinary matter constitutes a mere 5% of the total energy and matter content of the universe. We are the rare, luminous froth on the surface of a deep, dark sea. Let us sit with this number for a moment. 5%. All the hundreds of billions of galaxies, each with hundreds of billions of stars, all the glowing nebulae, all the planets and moons and asteroids, every single atom of it, adds up to just 1/20th of what is actually out there. It is a humbling statistic that reframes our place in the cosmos. We are not the main event. We are a delicate, intricate, and beautiful side effect. But what a precious side effect it is. For within this 5% lies all complexity, all chemistry, all the potential for suns to shine and life to arise. It is the universe made visible, the part that tells a story through light. So what is this ordinary stuff? At its heart, it is the matter composed of atoms, which are in turn made of protons, neutrons, and electrons. Protons and neutrons belong to a family of particles called baryons, hence the term baryonic matter. These particles interact through all four fundamental forces: gravity, electromagnetism, the strong nuclear force that binds atomic nuclei, and the weak nuclear force responsible for certain types of radioactive decay. It is this rich ability to interact, to emit and absorb light, to clump into molecules, to form complex structures, that makes ordinary matter so visually and chemically vibrant. It is the matter that engages in the grand conversation of the cosmos, speaking in the language of photons. Its journey began in the furnace of the Big Bang. In the first 3 minutes, as the universe cooled from its unimaginably hot, dense beginning, protons and neutrons formed and fused to create the lightest nuclei: hydrogen, helium, and traces of lithium. This primordial soup, about 75% hydrogen and 25% helium by mass, was the seed stock for everything to come. For hundreds of millions of years, the universe was dark, filled only with this vast, expanding cloud of neutral gas, punctuated by the invisible gravitational seeds of dark matter. Then gravity began to pull the gas into the first structures. Where it pooled and condensed, pressure and temperature soared, and nuclear fusion ignited. The first stars were born, and with them, light returned to the universe. These first stars were the universe's great alchemists. Within their searing cores, they fused the primordial hydrogen and helium into heavier elements: carbon, oxygen, nitrogen, iron. When these massive, short-lived stars ended their lives in spectacular supernova explosions, they forged even heavier elements and scattered this newly created star stuff back into the cosmos. This enriched gas, now containing the elements of planets and life, coalesced into later generations of stars. Our own sun is a third or fourth generation star, born from a cloud that had been seeded with the ashes of countless stellar ancestors. Every atom of oxygen you breathe, every atom of carbon in your cells, every atom of calcium in your bones was forged in the heart of a star that lived and died long before our solar system was a swirl of dust in a spiral arm. We are literally children of the stars. This ordinary matter exists in several states across the cosmos. Most of it is not in stars, but in a diffuse, hot form known as the intergalactic medium, a tenuous soup of ionized gas that fills the space between galaxies in the cosmic web. Another significant portion resides as warm or cold gas and dust within galaxies, the raw material for future stars. A much smaller, but to us incredibly significant fraction has been locked into stars, planets, asteroids, and comets. And an infinitesimally tiny sliver of that fraction has organized itself into the phenomenon we call life. As you rest, consider the journey of the atoms that make up your hand. Some of the hydrogen atoms may be truly primordial, unchanged since the first 3 minutes of cosmic time. The heavier elements have a more dramatic history. Born in stellar cores under immense pressure, blasted across light years in supernova shockwaves, drifting for eons in molecular clouds, before finally coming together in the protoplanetary disk that formed Earth. They have been part of mountains and seas, of ancient microorganisms and giant reptiles, cycling through the biosphere for billions of years until this moment, where they form part of a being capable of contemplating its own cosmic origins. This connectivity is a profound source of peace. You are not separate from the universe. You are a temporary, conscious assemblage of its most ancient, well-traveled materials. This 5% is what we know best, yet its scarcity in the cosmic budget is a constant reminder of how much lies beyond our direct perception. It teaches us that the universe is far stranger and more wonderful than it appears. The ordinary matter is the part that glows, that sings in wavelengths we can detect. It allows us to trace the outlines of the dark, to infer the presence of the vast, unseen 95% through its gravitational and expansive effects. We are the sensitive tip of the cosmic iceberg, a small, bright region of a much larger, hidden reality. And as we have traced the story of this ordinary matter from the Big Bang to the present, we must now journey back to that very beginning, to the event that set this entire majestic, unfolding process into motion. To the moment where time, space, and all the ingredients of our reality emerged from a singularity of infinite potential, the Big Bang. We have followed the story of matter from our hands back to the stars, and from the stars back to the primordial clouds of hydrogen and helium. But where did this primordial soup itself come from? What is the source of the stage, the actors, and the script? To answer this, we must perform the ultimate act of cosmic rewinding. We must take the present expansion of the universe and trace it backward, like watching a film in reverse, compressing galaxies, stars, and atoms until all the energy and matter of the cosmos converges into a point of unimaginable density and temperature. This is not the start of a journey in space, but the beginning of space itself. This is the moment we call the Big Bang. Let us gently correct a common image. The Big Bang was not an explosion in space. like a cosmic firecracker detonating in a pre-existing void. It was the rapid expansion of space and time itself. There was no outside, no empty void waiting to be filled. Space, time, and all the energy of the universe emerged together from a state known as a singularity, a point where our current laws of physics break down, where concepts like where and when cease to have meaning. So, rather than picturing a blinding flash in the dark, imagine instead the sudden, graceful unfurling of reality from an infinitely dense, hot seed. A more fitting metaphor might be the surface of a balloon inflating from a pinprick. Every point on the surface moves away from every other point, and the surface itself is the entirety of their universe. Our story begins at time zero, but our scientific understanding can only take us back to an unimaginably early moment. The Planck epoch, named for physicist Max Planck. This is the first tick of the cosmic clock, 10 to the power of negative 43 seconds after the beginning. The universe was smaller than a subatomic particle, and conditions were so extreme that the four fundamental forces we know today, gravity, electromagnetism, and the strong and weak nuclear forces, were likely unified into a single primal superforce. It is a realm of pure quantum gravity, a frontier where our current theories fade into speculation, a silent, seething origin point shrouded in mystery. Then, from this unity, something extraordinary happened. In the first fraction of a second, the universe underwent a period of incomprehensibly rapid expansion known as cosmic inflation. Think of it as a moment of exponential stretching, where space itself expanded faster than the speed of light. In less than a billionth of a trillionth of a trillionth of a second, a region smaller than a proton was inflated to a size larger than our entire observable universe today. This inflation did several crucial things. It took the tiny, random quantum fluctuations that flickered in the primordial foam and stretched them to macroscopic scales. These stretched fluctuations became the slight variations in density, the seeds around which gravity would later gather dark matter and gas to form galaxies and the cosmic web. Inflation also explains why our universe appears so uniform and flat on large scales. It ironed out any initial wrinkles, leaving behind the smooth, isotropic cosmos we observe in every direction. As inflation ended, its immense potential energy flooded the universe, reheating it into a hot, dense plasma of fundamental particles, a bubbling soup of quarks, gluons, electrons, and photons. This is the hot Big Bang phase proper. Time is now a mere microsecond old. The universe is a searing broth, far too hot for even protons and neutrons to form. Quarks and gluons, the building blocks of protons and neutrons, move freely in what is called a quark-gluon plasma. As expansion continues and the universe cools, these quarks begin to bind together, pulled by the strong nuclear force. By around 1/10,000th of a second, protons and neutrons have frozen out from the cooling quark soup. For the next few minutes, the universe is a nuclear fusion reactor. Protons and neutrons collide and fuse in the intense heat, forming the nuclei of the lightest elements. Hydrogen, a single proton, helium, 2 protons and 2 neutrons, and trace amounts of lithium and deuterium. This process, known as Big Bang nucleosynthesis, lasted only about 17 minutes before the expanding universe cooled and thinned too much for fusion to continue. It left behind a universe composed of about 75% hydrogen nuclei and 25% helium nuclei, a ratio that matches what we observe in the oldest, most pristine corners of space, a powerful piece of evidence for this entire early narrative. For the next 380,000 years, the universe remained a hot, opaque fog. It was filled with a plasma of positively charged atomic nuclei and free electrons, constantly scattering the photons of light that zipped among them. Light could not travel freely. It was trapped, bouncing from particle to particle like headlights in a thick, glowing mist. The universe was a luminous, diffuse glow, but with no clear lines of sight. Then, at the epoch of recombination, the universe cooled below 3000 Kelvin. This allowed electrons to be captured by the atomic nuclei, forming stable, neutral hydrogen and helium atoms for the first time. Suddenly, the photons, which had been trapped in the charged plasma, were set free. They could now travel across the universe unimpeded. This moment of liberation is the source of our most profound cosmic snapshot, the cosmic microwave background radiation. But that is a story for the next quiet chapter. As you rest, let the scale of this genesis settle not as a violent cataclysm, but as a profound and graceful unfolding. Every law of physics, every constant of nature, was set during these initial moments. The strength of gravity, the charge of an electron, the nuclear forces, these were not arbitrary, but emerged from the breaking of the primordial symmetry. Had they been different by even a minuscule fraction, atoms would not be stable, stars would not shine, and the complex chemistry of life would be impossible. We are the beneficiaries of a breathtakingly precise calibration, written into the fabric of the cosmos in its first fleeting instance. The Big Bang is not a distant explosion. It is the ongoing story of expansion in which we are still embedded. The space between galaxies is still stretching. The faint afterglow of that first light still bathes us. We are not just living in the universe. We are living inside the Big Bang, riding its gentle outward wave some 13.8 billion years after it began. And on that wave, traveling to us from the very edge of visibility, comes the oldest picture in existence, a baby photo of the cosmos, a faint, cold whisper from the dawn of time. For 380,000 years after the Big Bang, the universe was a luminous, opaque fog. And then, in a cosmic moment of clarity, it became transparent. The trapped light was finally set free. That first flash, that initial burst of photons streaming into the newly opened cosmos, has been traveling ever since. But it has not remained a flash. The relentless expansion of the universe has stretched space itself over the intervening 13.8 billion years, and in doing so, it has stretched those ancient photons too. Their wavelengths have been pulled, lengthened, and transformed from visible light into microwaves. Today, that primordial light fills every cubic centimeter of the universe as a faint, cold, nearly uniform glow. We call it the cosmic microwave background radiation, or CMB. It is the oldest light we can see, the afterglow of creation, and it carries within its subtle patterns the baby picture of the universe. Imagine tuning an old analog television to a channel of static. That hiss and snow you see and hear, roughly 1% of that chaotic signal is the CMB photons that have journeyed since the end of the universe's dark age, now reaching your antenna as a whisper from the dawn of time. It was discovered accidentally in 1965 by Arno Penzias and Robert Wilson, two radio astronomers puzzled by a persistent, uniform microwave noise coming from every direction in the sky. This noise, this omnipresent signal, turned out to be the most important cosmological discovery since Hubble's revelation of the expanding universe. It was the smoking gun for the Big Bang theory, the definitive evidence that our universe did indeed have a hot, dense beginning. But the CMB is more than just a uniform glow. It is a treasure map. When we look at it with exquisitely sensitive instruments like the Planck satellite, we see that it is not perfectly smooth. It is etched with tiny variations in temperature and isotropies on the order of 1 part in 100,000. These minute fluctuations, these slightly warmer and cooler patches, are the imprints of those primordial quantum seeds stretched by inflation. They represent the regions of slightly higher and lower density in the early plasma. The denser, warmer spots would, over hundreds of millions of years, become the gravitational wells into which dark matter and gas would flow, eventually giving birth to the galaxies and clusters we see today. In the CMB's modeled pattern, we are seeing the blueprint for the entire large-scale structure of the cosmos. We are reading the initial conditions of the universe. Let's visualize this moment of liberation, the epoch of recombination, a little more closely. Picture the universe, now 380,000 years old, as a vast, hot, orange-red glow. Electrons and atomic nuclei are finally combining to form neutral atoms. As each electron is captured, a photon is released like a prisoner being set free. Suddenly, the fog clears. The universe, which was once an impenetrable plasma, becomes as transparent as a clean pane of glass. Those newly freed photons begin their endless journey. The moment you see a patch of the CMB from a particular direction, you are looking back along a straight line to the precise location in space and time where that photon last scattered off an electron 13.8 billion years ago. It is the ultimate cosmic horizon, the wall of last scattering. We cannot see beyond it with light because before that time, the universe was opaque. The CMB is the veil at the edge of our visible universe. There is a profound intimacy to this radiation. It is not just out there. It is here, passes through this room, through you as you listen. Its photons have been traveling since before our galaxy existed, since before any star in our galaxy was born. They have witnessed the entire history of cosmic structure formation, flying unscathed through the births and deaths of stars, the collisions of galaxies, the quiet growth of voids, and they carry that history in their subtle properties. By studying the precise statistics of its temperature fluctuations, cosmologists have been able to determine the age, composition, geometry, and fate of the universe with remarkable precision. The CMB tells us the universe is flat, that it contains about 5% ordinary matter, 27% dark matter, and 68% dark energy. Confirms the timeline of the Big Bang. It is our most reliable cosmic oracle. As you rest, consider this gentle bath of ancient light. It is a constant, quiet reminder of our origins. In its near-perfect uniformity, we see the profound unity of the cosmos. Every direction on the largest scales is essentially the same. In its tiny imperfections, we see the origin of all diversity, the seeds of galaxies, stars, planets, and life. Connects us directly to the infant universe. The photons warming a patch of interstellar dust, the photons hitting a radio telescope, and the photons harmlessly passing through your body right now are all siblings from that same moment of transparency. They are the universe's first light, grown faint and cold with age, telling its story to anyone who learns to listen. It is a story that began in a hot, dense state, but where does it go from here? The CMB gives us the starting conditions, But the universe's ultimate fate is written by the interplay of the ingredients it helped us measure: the relentless pull of gravity and the mysterious push of dark energy. As the afterglow fades further into longer wavelengths and colder temperatures with each passing eon, it quietly points us toward the distant future, inviting us to contemplate how this grand, unfolding story might one day end. From the ancient, fading whisper of the cosmic microwave background, we have looked back to the beginning. Now, let us turn our gaze forward, along the trajectory set by that initial expansion and shaped by the dark ingredients we have met. The universe has a future, a destiny written in the interplay between the relentless pull of gravity and the persistent push of dark energy. Contemplating this future requires us to stretch our minds across timescales that make the age of the universe seem like a single breath, trillions upon trillions of years. It is a meditation not on endings, but on the long, slow rhythms of cosmic evolution. The possibilities are not violent finales, but gradual transformations, each with its own quiet, profound poetry. The leading scenario, supported by our current measurements of dark energy, is often called the Big Freeze or heat death. Imagine the expansion of the universe, gently accelerated by dark energy, continuing forever. Galaxies not already bound together by gravity will see the space between them stretch at an ever-increasing rate. Over hundreds of billions of years, the observable universe from any given point will shrink, as more and more galaxies are redshifted beyond visibility. The cosmos outside our gravitationally bound local group of galaxies will fade to black. Star formation, which relies on dense clouds of gas, will eventually cease as galaxies are stripped of their raw materials and remaining gas is either locked up in dead stars or dispersed into an ever-thinning intergalactic medium. One by one, the stars will burn out. First the massive, brilliant blue ones, then stars like our Sun, and finally, the slow-burning red dwarfs, whose faint glow may last for trillions of years. The universe will become a darker place, populated by the cooling remnants of stars. White dwarfs, neutron stars, and black holes. On even longer timescales, through processes so slow they are almost static, even these remnants may evaporate or decay. The universe will approach a state of maximum entropy, a uniform, isotropic sea of incredibly dilute particles and radiation, where the temperature approaches absolute zero and no energy gradient remains to do any work. It is a quiet, deep chill, a state of equilibrium and ultimate rest. There is a strange tranquility in this vision. It is the universe winding down, exhaling completely, and finding a final, frozen peace. But our understanding of dark energy is not complete. What if its properties change over time? Another family of possibilities arises if the repulsive force of dark energy were to weaken or reverse. In this scenario, gravity could eventually reassert its dominion. The expansion of the universe would slow, halt, and then reverse. Galaxies would begin to draw closer together. This is the Big Crunch, a mirror image of the Big Bang. Over billions of years, the cosmos would contract, temperatures and densities rising as all structure is compressed. If the contraction continued all the way, the universe could collapse back into a hot, dense singularity, a potential endpoint, or perhaps a rebirth. This idea leads to the Big Bounce, a cyclical model of the cosmos. In this vision, the universe undergoes endless cycles of expansion and contraction, a cosmic inhalation and exhalation. Each Big Bang is preceded by a Big Crunch, from a previous cycle. The laws of physics might be reconfigured with each bounce, giving rise to new universes with different constants and possibilities. This is a deeply rhythmic, almost reassuring vision. A universe with no true beginning or end, but an eternal, pulsing rhythm of creation and dissolution, like the gentle, endless waves on a shore. There is a third, more dramatic possibility tied to a particular form of dark energy known as phantom energy. If the density of dark energy were to increase over time, its repulsive force would grow stronger and stronger, not just accelerating the expansion, but making the expansion rate itself increase exponentially. Eventually, this accelerating force would overcome all bound structures, not just galaxy clusters, but individual galaxies, solar systems, planets, and even atoms. This is the Big Rip. In this scenario, the very fabric of space-time would be torn apart. First, galaxy clusters would be ripped asunder, then individual galaxies. As the rip time approaches, stars would be pulled from their galaxies and planets from their stars. In the final, cataclysmic moments, the forces holding atoms and atomic nuclei together would be overcome. Every bit of matter in the universe would be torn into its most fundamental, disconnected components. While this sounds violent, it is important to remember it is a speculative idea on the furthest edge of possibility, requiring a form of dark energy for which we currently have no evidence. It serves as a reminder of how profoundly the unknown nature of dark energy dictates our long-term fate. As you rest with these vast possibilities, find comfort not in choosing one, but in the act of contemplation itself. Our current best evidence strongly points toward the big freeze, a slow, gentle fading. This future is not something to fear. It is the natural conclusion of the cosmic processes we see at work today. It is a future of profound quiet, a universe fulfilling its thermodynamic destiny over timescales so vast they render human history dimensionless. We live in a privileged cosmic moment. We exist during the bright, structured daytime of the universe, some 13.8 billion years after the beginning, when stars still shine, galaxies still spin, and the night sky is a tapestry of light. We are observant enough to trace our history back to a hot, dense beginning and to peer forward into a cold, expansive future. We exist in the sweet spot between the dominance of matter and the dominance of dark energy, in the epoch where the cosmos is both knowable and beautiful. This present moment, your moment of listening, is a fleeting, precious spark of consciousness in the long cosmic story. A story that, regardless of its final chapter, is one of majestic, patient transformation. And within this grand story of the cosmos, there exist phenomena of such extreme density and power that they bend the rules of reality itself. Places where gravity becomes an all-consuming force, and where the fabric of space-time is tied into knots. These are the universe's most enigmatic landmarks, black holes. In our journey through the cosmos, we have sailed past grand structures and contemplated invisible forces. Now we drift toward one of the universe's most profound mysteries, a place where the normal rules of physics soften and fade, where gravity becomes the ultimate sovereign. This is the realm of the black hole, not a cosmic vacuum cleaner or a raging monster of lore, but a serene, profound punctuation mark in the sentence of space-time. A black hole is a region of space where gravity is so intense that nothing, not even light, can escape its pull. It is the point where a massive star has exhausted its nuclear fuel, collapsed under its own weight, and crossed a threshold of density from which there is no return. Think of it not as a hole, but as an infinitely deep well in the fabric of the universe, a place where matter has been compressed to a point of infinite density called a singularity, shrouded by an invisible boundary known as the event horizon. The event horizon is the point of no return. It is not a solid surface, but a mathematical boundary, a spherical shell marking the division between the universe we know and the unknowable interior. Once anything crosses this threshold, all paths lead inward to the singularity. From the outside, we can never receive a signal, a particle, or a photon from inside the event horizon. It is the ultimate cosmic veil. But contrary to popular imagery, falling toward a black hole would not necessarily be a violent, torturous experience, at least not until the very end. If you were to approach a sufficiently large black hole, like the supermassive ones at galactic centers, the gravitational pull across your body would be so uniform that you could cross the event horizon without even noticing it, a transition marked by no flash of light, no sudden jerk. The true drama, known as spaghettification, occurs as you get closer to the singularity, where the difference in gravity between your head and feet becomes so extreme that you are stretched into a long, thin strand of atoms. But for a large black hole, this happens well inside the event horizon, hidden forever from the external universe. Black holes come in different scales. Stellar mass black holes, weighing a few to tens of times the mass of our sun, are the remnants of massive stars that ended their lives in supernova explosions. Then there are the supermassive black holes, behemoths millions or even billions of times the mass of the sun, which reside at the heart of nearly every large galaxy, including our own Milky Way. We do not yet fully understand how these giants grew so large, but they seem to be inseparable from the galaxies that host them, playing a crucial role in galactic evolution. Their immense gravity can govern the orbits of nearby stars and, when active, heat infalling gas to millions of degrees, causing it to glow brilliantly as a quasar or an active galactic nucleus, the brightest persistent objects in the universe. Yet, the black hole itself remains dark, a silent anchor at the core of the storm. Perhaps the most soothing thought about black holes is their beautiful simplicity. An isolated black hole, according to the laws of general relativity, can be completely described by just three properties: its mass, its electric charge, and its spin. This is known poetically as the no-hair theorem, suggesting that black holes have no complicated hair-like surface features. All other information about the matter that fell in, the type of atoms, their structure, their history, is lost to the outside universe. It is as if the black hole is a cosmic eraser, simplifying the incredibly complex into a pure state defined by only a few numbers. This leads to profound puzzles about the nature of information and entropy, but for our quiet contemplation, it offers a sense of minimalist elegance. The universe, in its most extreme state, reduces complexity to a few fundamental parameters. While we cannot see a black hole directly, we can observe its influence. We see stars orbiting an invisible, massive object at the center of our galaxy. We see disks of superheated gas, called accretion disks, swirling around black holes at nearly the speed of light, their friction generating intense X-rays. And most remarkably, in 2019, we were given a glimpse of a black hole's shadow. The Event Horizon Telescope, a global network of radio observatories, produced an image of the supermassive black hole at the center of the galaxy M87. What we see is not the black hole itself, but the glowing ring of hot gas orbiting it, with a dark central region, the shadow of the event horizon, where light is swallowed. It is a breathtaking confirmation of our theories, a portrait of gravity made visible. As you rest, consider the black hole not as an agent of destruction, but as a natural part of the cosmic cycle. They are the final resting place for the most massive stars, the regulators at the hearts of galaxies, and perhaps even the seeds from which galaxies first grew. In their profound darkness, they represent a boundary of human knowledge, a reminder that our understanding of reality is still unfolding. Their existence stretches our imagination and grounds us in the elegant, if sometimes unfathomable, laws of physics. And just as black holes warp space and time, their violent interactions can create ripples in the very fabric of the cosmos. Ripples that travel across billions of light years to gently shake the Earth, bringing us news of catastrophic events in the distant universe. These are gravitational waves, the next whisper on our journey. From the absolute dark of the black hole, let us turn to an object that is its slightly less extreme cousin. A place where matter is pressed to the very brink of becoming a black hole, but manages to hold the line through a fascinating quantum stalemate. This is the neutron star, the dense, crystalline corpse of a massive star that lacked the final heft to collapse into a true singularity. When a star between about 8 and 20 times the mass of our Sun reaches the end of its life, it does not go quietly. It explodes as a supernova, blasting its outer layers into space in a spectacular display that, for a few weeks, can outshine an entire galaxy. What remains behind is no longer a star powered by fusion, but a city-sized sphere of unimaginable density, a neutron star. To grasp this density, let us play with a gentle metaphor. Imagine taking all the people who have ever lived on Earth, roughly 117 billion souls, and compressing them. You would have a sphere of organic matter a few hundred meters across. Now, compress the entire mass of our Sun, a sphere 1.4 million kilometers in diameter, into a ball just 20 kilometers across, the size of a small city. This is a neutron star. A single sugar cube-sized volume of its material would weigh about 1 billion tons on Earth, as much as a mountain. This staggering density is the result of gravity overcoming all other forces. In the final moments of the supernova collapse, the immense pressure forces electrons and protons together, merging to form neutrons and neutrinos. The star becomes a vast nucleus, a sea of neutrons packed shoulder to shoulder, with a thin, solid crust of iron nuclei possibly floating on top. It is matter stripped to its most essential neutral form. The physics within a neutron star is a realm of delightful extremes. The gravity at its surface is about 200 billion times stronger than Earth's. If you were to drop a marshmallow onto its surface from a meter above, it would hit with the energy of a nuclear bomb, transformed by the tremendous acceleration. The interior is a mystery, a place where familiar concepts of solid, liquid, and gas break down. Physicists speak of nuclear pasta, where densities are so high that atomic nuclei are squeezed into long rods and sheets, resembling spaghetti and lasagna. Deeper still, the neutrons may become a superfluid, a frictionless quantum liquid that can flow without any viscosity. At the very core, even the neutrons might break down into a soup of their constituent quarks, creating a quark star within a star. Each neutron star is a unique laboratory for states of matter that cannot be recreated anywhere else in the universe. Now, take this incredible spinning sphere and give it a magnetic field. Not just any magnetic field, but one 1,000,000,000,000 times stronger than Earth's, and set it spinning not once a month like our moon, but hundreds of times per second. This combination, rapid rotation and an immense magnetic field, gives birth to one of the cosmos's most precise and poetic phenomena, the pulsar. A pulsar is a neutron star that beams radiation from its magnetic poles. Because the magnetic axis is often tilted relative to the spin axis, these beams sweep through space like the ray of a cosmic lighthouse. If Earth happens to lie in the path of that sweeping beam, we detect a regular pulse of radiation, radio waves, X-rays, or gamma rays, with a timing so exact it rivals the best atomic clocks. The pulse can arrive every few milliseconds or every few seconds, a metronome of breathtaking regularity. The first pulsar discovered in 1967 by Jocelyn Bell Burnell was initially nicknamed LGM-1 for Little Green Men, because the signal was so precise it was thought it might be an artificial beacon. We now know it as the natural heartbeat of a distant stellar remnant. Pulsars are the universe's timekeepers. Their steady pulses allow astronomers to probe the fabric of space-time itself, to detect the subtle gravitational waves from orbiting black holes, and to map the Milky Way. The regularity is so dependable that scientists have proposed using a network of pulsars as a galactic positioning system for future interstellar navigation, a celestial lighthouse network guiding ships across the ocean between the stars. Some neutron stars push extremes even further. Magnetars are a rare class of neutron stars with magnetic fields 1,000 times stronger still. So powerful they can literally crack the star's rigid crust, causing starquakes that release colossal bursts of gamma rays and X-rays. These bursts, observed from across the galaxy, are among the most energetic magnetic events in the universe. They remind us that even in this cold, dense remnant, there is immense pent-up energy, a final fierce expression of the star that once was. As you rest, consider the neutron star, a testament to balance. It is a star that defeated total gravitational collapse not by fusion, but by the simple, stubborn fact that neutrons cannot be squeezed any further without becoming something else. They represent nature's ultimate compression, a state of being so dense that it bends light and warps space-time around it. And the pulsar, that spinning beacon, sings a song of constancy across the light years. Its pulse is a gentle, rhythmic reminder of order amidst cosmic chaos, a signal that some things, even in the aftermath of catastrophic stellar death, can achieve a perfect, predictable spin. They are the universe's stopwatches and its lighthouses, guiding our understanding and marking the slow, steady passage of deep time. And just as a spinning neutron star can create beams of light, the most violent motions of massive objects in the universe, like two neutron stars or black holes spiraling together, can create ripples in space-time itself. These ripples carry a different kind of signal, one not of light, but of gravity. They allow us to hear, for the first time, the collisions that shape the cosmos. For all of human history, we have been children of light. We have understood the cosmos by collecting photons, particles of light, with our eyes and our telescopes, painting a picture of the universe from the colors and intensities of electromagnetic waves. But light can be blocked, scattered, or absorbed. It shows us only the surface of things. In 2015, a new sense opened. We learned to listen, not with microphones, but with instruments so precise they can detect a distortion in space-time itself smaller than the nucleus of an atom. We learned to hear the universe through gravitational waves, ripples in the fabric of spacetime caused by the most violent and energetic events in the cosmos. These are not sound waves traveling through air, but literal waves in the four-dimensional continuum of the universe, stretching and squeezing space itself as they pass. The story of this discovery begins a century ago with Albert Einstein. His theory of general relativity reimagined gravity not as a force, but as the curvature of spacetime caused by mass and energy. A massive object, like the Sun, creates a depression in this fabric, and planets move along the curved paths, like marbles rolling in a bowl. Einstein's equations also predicted that when massive objects accelerate, particularly when they move in an asymmetric, spiraling dance, they would generate waves that propagate outward at the speed of light, warping the geometry of space as they go. Einstein himself was unsure if these waves were physically real or mere mathematical artifacts. For decades, they remained a theoretical curiosity. Then came the vision to build an instrument sensitive enough to catch these infinitesimal ripples. The result was LIGO, the Laser Interferometer Gravitational Wave Observatory. Imagine two identical perpendicular arms, each 4 kilometers long, carved into the Earth. A laser beam is split and sent down each arm, bouncing off mirrors at the end to return and recombine. In perfectly still spacetime, the light waves return in sync and cancel each other out. But if a gravitational wave passes through, it will stretch one arm and squeeze the other, just for a fraction of a second, changing the distance the light travels by a minuscule amount. This causes the recombined laser light to flicker. On September 14, 2015, LIGO detected that flicker. The signal, named GW150914, was the chirp of 2 black holes, one about 36 times the mass of the Sun, the other 29, spiraling together and merging 1.3 billion light-years away. In a fifth of a second, they converted an amount of mass equivalent to 3 suns into pure gravitational wave energy, momentarily shaking the fabric of spacetime with more power than all the stars in the observable universe combined. And we felt it. What does it mean to hear this event? The signal, when converted into sound, is a quick upward sweep in frequency, a chirp that rises from about 35 Hz to 250 Hz in less than a second, ending in a final ringing tone as the single merged black hole settles into a smooth sphere. It is the sound of spacetime ringing like a bell. Since that first detection, LIGO and its European counterpart Virgo have heard many more cosmic events. More black hole mergers, and in 2017, the merger of 2 neutron stars. That neutron-star collision was a watershed. It was not only heard in gravitational waves, but also seen across the electromagnetic spectrum, gamma rays, light, radio waves, confirming that such mergers are the cosmic forges where heavy elements like gold, platinum, and uranium are created. The gold in your wedding ring was likely born in the furious collision of 2 neutron stars, billions of years ago, its story now told through both light and ripples in space. Gravitational wave astronomy is profoundly different from light-based astronomy. Light can be absorbed or reflected. Gravitational waves pass through almost everything unimpeded. They offer a clear, direct view of the event itself, the dynamics of spacetime in the violent final moments of a merger. They allow us to probe the nature of gravity itself in its most extreme regime, testing whether Einstein's theory holds true near black holes. And they reveal a population of black holes we never knew existed. Stellar mass black holes far heavier than we thought possible, silent and dark until they dance with a partner. As you rest, consider the gentle nature of these waves. By the time they reach us from these cataclysms, their effect is incredibly subtle. They are a whisper of distortion, a sigh in the structure of reality. Their detection is a triumph of human curiosity and engineering, a testament to our desire to understand the universe through every means possible. We are no longer silent observers of a cosmic light show. We are now listeners in a grand symphony, hearing the slow, deep rhythms of massive bodies moving through the gravitational field. The universe speaks in many languages: light, neutrinos, cosmic rays, and now we have learned to understand the language of space-time itself. This new sense reveals a cosmos filled with invisible, dynamic events, a universe constantly aquiver with the distant motions of its most massive inhabitants. And as we listen to the grand, gravitational symphony of stars and black holes, our curiosity naturally turns to other, quieter questions. Among the trillions of planets that must orbit these stars, could there be other islands of calm, other places where the universe has become complex, layered, and perhaps even alive? This wonder leads us to search for new worlds, far beyond our own solar system. After listening to the deep, gravitational songs of black holes and neutron stars, our journey turns to a quieter, more intimate search. We shift our focus from the massive and the extreme to the small, the rocky, the temperate, and the potential for calm harbors in the cosmic dark. For most of human history, we knew of only one family of planets, our own solar system. The idea of other worlds orbiting distant stars was a fantasy of philosophers and science fiction writers. But in the last 3 decades, fantasy has become fact. We have entered the age of exoplanets, planets orbiting stars other than our sun, and the numbers are both humbling and exhilarating. As of now, we have confirmed over 5,000 of these distant worlds, and the count grows regularly. The galaxy, it seems, is teeming with planets. This discovery fundamentally changes our understanding of our place in the universe, suggesting that solar systems are not rare anomalies, but a common, even inevitable part of stellar evolution. The methods used to find these hidden worlds are feats of subtle ingenuity. The most productive technique is the transit method. Imagine a distant star, its light steady. If a planet orbits that star and, from our vantage point, passes directly in front of it, the planet will block a tiny fraction of the star's light. This causes a minuscule, periodic dip in the star's brightness. For a planet like Earth transiting a sun-like star, the dip is a mere 0.01%, like detecting the shadow of a gnat crossing a searchlight from thousands of miles away. Space telescopes like Kepler and TESS are designed to monitor hundreds of thousands of stars simultaneously, their sensitive instruments patiently recording these almost imperceptible winks. Another method, the radial velocity method, detects the star's subtle wobble caused by the gravitational tug of an orbiting planet. As the planet pulls the star's light is very slightly blue-shifted and red-shifted in a regular rhythm. These techniques, among others, have revealed a stunning diversity of worlds. Hot Jupiters orbiting blisteringly close to their stars, mini-Neptunes, super-Earths, and planets in binary or even triple star systems. Amidst this menagerie, our search is guided by a profoundly human question. Could any of these worlds be habitable? Could they support liquid water, stable climates, and perhaps even life? This leads us to the concept of the habitable zone, often poetically called the Goldilocks zone. It is the orbital region around a star where conditions are just right, not too hot and not too cold, for liquid water to exist on a planet's surface. For our Sun, this zone is a relatively narrow band where Earth happily resides, with Venus lying too close, too hot, and Mars lying a little too far, too cold. But the habitable zone is not a simple, fixed distance. It depends on the star's temperature and luminosity. A small, cool red dwarf star has its habitable zone much closer in, while a large, hot blue giant zone is vastly more distant. A planet in the habitable zone is a promising candidate, but it is no guarantee of paradise. The planet must also have a suitable atmosphere to retain heat and regulate temperature, a stable orbit, and likely a protective magnetic field to shield it from stellar radiation. It is a delicate balance of many factors. The Kepler mission, in particular, gifted us with a statistical revelation that small, rocky planets like Earth and Venus are likely the most common type of planet in the Milky Way. Based on Kepler's data, astronomers estimate there could be billions of Earth-sized planets orbiting in the habitable zones of their stars in our galaxy alone. Let that number settle gently in your mind. Billions of potential havens. Each is a world with its own history, its own landscape, its own sky. Some may be water worlds, completely covered by global oceans. Others may be arid, rugged deserts. Some may have thick, Venus-like atmospheres, while others may have thin, Mars-like air. A fraction of those may have conditions that allow for chemistry complex enough to give rise to life. We do not yet know, but the sheer probability is a quiet, hopeful bell ringing in the cosmic silence. As you rest, consider the patience and optimism of this search. It is a testament to our species' enduring curiosity about companionship in the cosmos. Every faint dip in starlight, every subtle stellar wobble, is a clue in the greatest detective story ever conceived. The upcoming generation of telescopes, like the James Webb Space Telescope, will begin to study the atmospheres of some of these promising worlds, looking for chemical biomarkers, signatures of gases like oxygen, methane, or ozone that, in combination, might suggest biological activity. We are on the cusp of potentially revolutionary discoveries. Yet, in this vast field of possibilities, our own Earth emerges not as mundane, but as miraculously rare in its precise combination of stability and richness. We have a large, stabilizing moon. We have a protective giant planet, Jupiter, that helps clear debris from the inner solar system. We have a magnetic field, plate tectonics that recycle carbon, and a remarkably stable star. The existence of billions of potential Earths does not diminish our world. It highlights the exquisite, fragile convergence of conditions that allowed life to flourish here for so long. It deepens our appreciation for the pale blue dot we call home. This search for other islands of life naturally leads to a deeper, more philosophical question. If the universe is so vast and so old, and if planets are so common, then where is everybody? This simple, profound inquiry is known as the Fermi paradox, and it invites us to contemplate not just the astronomy of other worlds, but the potential sociology and future of consciousness in the cosmos. It is a gentle puzzle that leads us from the science of discovery into the realm of wonder and possibility. We have sailed past distant worlds, counted potential havens in the billions, and felt the thrilling possibility that we are not alone. Yet, the cosmos presents us with a profound and gentle puzzle. The universe is inconceivably vast, about 13.8 billion years old, and filled with an abundance of stars and planets. The ingredients for life, carbon, water, organic molecules, are everywhere, scattered by asteroids and stellar winds. Given such immensity of space and time, it seems statistically almost inevitable that life should have arisen elsewhere, perhaps many times over. Some of that life may have evolved intelligence, technology, and the desire to explore or communicate. And yet, we see no one. We hear nothing. The universe appears, for all its splendor, to be profoundly, silently empty of other civilizations. This contradiction between the high probability of extraterrestrial intelligence and the stark lack of any evidence for it is known as the Fermi paradox, named for the physicist Enrico Fermi, who, over a casual lunch in 1950, is said to have asked simply, "But where is everybody?" The paradox is not a proof of our solitude, but an invitation to deep and peaceful reflection. It asks us to consider all the steps between the formation of a habitable planet and the emergence of a galaxy-spanning civilization, and to wonder which of those steps might be incredibly difficult, rare, or tragically fragile. Scientists have formalized some of these steps in the famous Drake equation, a framework that multiplies together a series of probabilities. The rate of star formation, the fraction of stars with planets, the number of habitable planets per system, the fraction where life actually emerges, the fraction where life becomes intelligent, the fraction that develops detectable technology, and finally, the length of time such a civilization broadcasts its existence into space. The result is N, the estimated number of communicative civilizations in our galaxy. The problem is, we only know the first few factors with any confidence. The later ones, involving biology, intelligence, and sociology, are complete unknowns. They could be very, very small numbers. This leads to the concept of the Great Filter, a hypothesized barrier that is so difficult to overcome that it explains the cosmic silence. The terrifying question is, where in the timeline does this filter lie? Is it behind us or ahead of us? If the filter is behind us, if the transition from non-living chemistry to simple life, or from simple life to complex, intelligent life is astronomically rare, then we are a glorious, improbable fluke and the silence makes sense. We may truly be alone or at least exceedingly rare. But if the filter is ahead of us, if the step from a technological civilization to a stable, long-lived, starfaring one is almost impossible, then the silence is ominous. It suggests that every civilization like ours eventually destroys itself, perhaps through nuclear war, environmental collapse, runaway technology, or some other catastrophe we have yet to imagine. In this view, the stars are not empty. They are graveyards of civilizations that failed to pass through the filter. Other resolutions to the paradox are less grim and more wondrous. Perhaps intelligent life is common, but it exists in forms or dimensions we cannot perceive. Perhaps they have advanced to a post-biological state, living as conscious clouds or within simulated realities, with no interest in physical exploration. Perhaps they practice a form of cosmic conservation or non-interference, choosing to remain silent to allow younger civilizations like ours to develop without influence, a concept often called the zoo hypothesis. Or perhaps the distances are simply too vast and the timescales too mismatched. A civilization might bloom for a mere 10,000 years, a flicker on a galactic scale, while its radio signals crawl at the speed of light across a galaxy that is 100,000 light-years wide. We could be like ships passing in an unimaginably vast, dark ocean, their lights too faint and distant to ever see one another. There is also the humbling possibility that our methods are still primitive. We have been listening for deliberate radio signals for less than a century, a blink in cosmic time. We may be looking for the wrong things, missing subtle, faster-than-light neutrino communications, or structured laser pulses, or engineering on scales we can't comprehend, like Dyson spheres harnessing a star's entire energy. Our search has only just begun. As you rest with this paradox, let it not be a source of anxiety, but of spacious wonder. It holds a mirror to our own civilization, highlighting both our fragility and our potential. It underscores the preciousness of our moment of awareness on this tiny planet. The silence is not necessarily a verdict of loneliness. It is a question written in the stars, and we are only now learning how to read. It invites humility, patience, and a long-term perspective. Our species is young. Our technological adolescence has been turbulent, but we are learning. The very act of listening, of building radio telescopes and pondering these questions, is a hopeful step. We are the universe beginning to wake up and call out, however softly, into the night. The Fermi paradox ultimately teaches us that the universe does not owe us answers. Its truths unfold on timescales that dwarf our own. The search itself is a noble, peaceful endeavor, a way to connect our deepest curiosities to the grandest of mysteries. Whether we find companionship or confirm a sublime solitude, the journey expands what it means to be human. And as we contemplate the possibilities of a single vast universe, our minds naturally stretch to an even more extravagant idea, that our universe, with all its galaxies and mysteries, might not be the only one. What if reality is a multiverse, a frothing sea of bubble universes, each with its own unique laws and stories? This is not science fiction, but a serious, if speculative, extension of our cosmological theories. A final, expansive horizon for our quiet exploration tonight. From the silent question of the Fermi paradox, our minds naturally stretch toward an even more expansive possibility. If one universe, with its hundreds of billions of galaxies, seems insufficient to answer the puzzle of our apparent solitude, what if our cosmos is but one note in a grander symphony? What if there is not one universe, but many? This is the speculative, mind-bending concept of the multiverse. It is not a proven scientific fact, but a serious theoretical consequence that emerges from several pillars of modern physics and cosmology. It is a frontier of thought, a place where science, philosophy, and imagination blend into a soft, shimmering horizon. Tonight, let us explore this idea not as a definitive truth, but as a gentle thought experiment, a way to stretch the canvas of reality and see what patterns might lie beyond its edges. The most well-grounded multiverse concept comes from the theory of cosmic inflation. Recall that brief exponential expansion in the universe's first moments. Inflationary theory suggests that this expansion may not have stopped everywhere at once. Instead, like a pot of water boiling eternally, inflation may continue in some regions while ending in others. Each region where inflation ends becomes a separate, isolated bubble universe, with its own Big Bang and its own subsequent evolution. Our entire observable cosmos would be just one such bubble in an endlessly inflating multiverse. In this inflationary multiverse, each bubble could have different physical properties. The fundamental constants, the strength of gravity, the mass of an electron, the cosmological constant, might be randomly set as each bubble forms. In most, these constants would likely be inhospitable to the formation of atoms, stars, or life. We find ourselves in a bubble where the numbers are just right because, well, we couldn't exist otherwise. This is a cosmic application of the anthropic principle. We observe a universe compatible with our existence because we are here to observe it. A second thread comes from quantum mechanics. The many worlds interpretation proposed by Hugh Everett suggests that every quantum event with multiple possible outcomes doesn't just randomly pick one. Instead, the universe splits or branches into multiple copies, one for each possible outcome. In this view, every choice, every random quantum decay, creates a new, equally real universe. There is a universe where you turned left instead of right, a universe where a different sperm fertilized the egg that became you, a universe where the dinosaurs never went extinct. This creates a near-infinite fractal tree of parallel realities, all stemming from the same quantum root. While profoundly different from the inflationary bubbles, both ideas share a theme. Our reality may be one of a vast ensemble. A third, even more abstract concept emerges from string theory and the idea of higher dimensions. In some formulations, our universe may be a three-dimensional brain, short for membrane, floating in a higher dimensional space, like a sheet of paper floating in a room. Other such brains could exist parallel to ours, each hosting its own universe, perhaps occasionally colliding or interacting in ways that could even explain our own Big Bang. This is the brain multiverse. What does contemplating the multiverse offer our quiet, earthbound minds? It is a gentle reminder of the breathtaking potential woven into the fabric of reality. It suggests that our universe, with all its specific, finely tuned laws that allow for galaxies and life, might not be a lonely, accidental miracle, but one possibility among a near-infinite array. Somewhere, in another bubble or on another brain, the laws of physics might be entirely different. There might be universes where gravity is repulsive, where time flows in loops, where there are 5 fundamental forces, or where space has 10 dimensions. There might be universes that are eternally contracting, or that are nothing but a uniform, timeless haze. The possibilities are limited only by the mathematics that describes them. Philosophically, it can be both a humbling and a liberating perspective. It relativizes our own existence, our struggles, triumphs, and histories, so all-consuming to us, are but one story in a library of stories too vast to ever read. Yet, it also amplifies the wonder of our particular story. In the unimaginable vastness of the multiverse, here we are in this universe, on this planet, conscious and curious, able to even conceive of such grand ideas. That in itself is a kind of magic. As you rest, let your mind drift at the edge of this concept. You don't need to believe it or understand its mathematics. Simply hold it as a soft, speculative light at the end of the tunnel of our knowledge. It represents the human mind's brave and beautiful refusal to be bound. We look at the single universe we see, and we dare to imagine a greater whole of which it is only a part. Whether such a multiverse is real or not, the act of imagining it expands our sense of the possible. It teaches us that our current reality, for all its majesty, might be just the first chapter or a single page in a book of cosmic possibility whose full scope we may never grasp. And as we consider our place within a possibly infinite ensemble of realities, we are brought back with a newfound sense of scale to a more immediate and profound question. Within our own specific, beautiful, and knowable universe, what is our true place? This brings us back from the edge of speculation to a cornerstone of scientific humility, the Copernican principle. From the dizzying prospect of infinite universes, we return, with a deep and quiet breath, to our own. To the one universe we know, the one we are part of, the one we can observe and measure and feel. And here, we confront a question that has transformed from theological inquiry to scientific cornerstone. What is our place in this cosmos? The answer, refined over centuries, is encapsulated in the Copernican principle. It is the profound and humbling idea that we do not occupy a privileged or central position in the universe. Our planet is not the center of the solar system, our sun is not the center of the galaxy, our galaxy is not the center of the universe, and even our universe in a multiverse scenario may be utterly ordinary. This principle is not a statement of our insignificance, but a celebration of the uniformity and knowability of the cosmos. It is the great leveler, the idea that allows us to apply the same physics everywhere, trusting that the laws we discover here are the laws that govern a quasar at the edge of visibility. The journey to this understanding was a slow, revolutionary unwinding of cosmic pride. For millennia, the Ptolemaic model placed Earth, and by extension humanity, at the literal center of creation. The heavens revolved around us in perfect, crystalline spheres. This was an intuitively pleasing, egocentric cosmology. Then, in the 16th century, Nicholas Copernicus proposed a heliocentric model, placing the sun at the center. It was a seismic shift, not just astronomically, but philosophically. We were demoted from the stage to one of the actors. Galileo's telescope provided evidence, and later, our understanding of the Milky Way galaxy showed our sun to be a speck in a vast wheel of stars. Edwin Hubble revealed that our galaxy was one of countless island universes. With each step, our imagined centrality evaporated. The Copernican principle became a guiding light for modern cosmology. We should assume our vantage point is typical, not special. This assumption of mediocrity has proven incredibly powerful. When we observe that all distant galaxies are receding from us, we don't conclude we're at the center of an explosion. We deduce the universe is expanding uniformly everywhere. Our non-special position is the key to understanding the whole. This principle extends to a statistical concept called the principle of mediocrity. It suggests that, in the absence of evidence to the contrary, we should assume our circumstances are common, not rare. Our sun is a typical G-type main sequence star. Our planet is a rocky world in a habitable zone. The elements that make us are the products of universal stellar nucleosynthesis. This principle drives the search for exoplanets and the expectation that life, if it arises, could be widespread. It is a tool of humility that fuels discovery. Yet, it exists in a fascinating tension with another, seemingly opposite idea, the anthropic principle. In its weak form, this principle simply states that we observe a universe compatible with our existence. Of course we do. If the constants of nature were even slightly different, atoms would not be stable, stars would not shine, and we would not be here to wonder about it. This is a selection effect, not a design, but it forces us to confront an astonishing fact. Our universe is remarkably fine-tuned for complexity. The strengths of the fundamental forces, the mass of the electron, the value of the cosmological constant, all seem calibrated within a razor-thin margin to allow for galaxies, stars, planets, and life. So, are we mediocrities or miracles? The multiverse hypothesis offers a potential resolution. In an infinite ensemble of universes with randomly varying constants, a tiny fraction will, by sheer chance, have the right numbers for life. We necessarily find ourselves in one of those. In this view, the Copernican principle holds on a grander scale. Our entire universe is a mediocre bubble among an infinite froth, but one that happens to have the right conditions for us. Without invoking a multiverse, the fine-tuning remains one of the deepest mysteries, a quiet song of precision written into the laws of physics. Amidst this dialogue between mediocrity and fine-tuning, a beautiful third perspective emerges, one voiced eloquently by the astronomer Carl Sagan. He acknowledged our physical non-centrality but proposed a different kind of significance. We are a way for the cosmos to know itself. This is a breathtaking inversion. The universe, through 13.8 billion years of evolution, through the formation of stars and galaxies, the forging of heavy elements, the complex chemistry on a stable planet, has produced a conduit for self-awareness. In us, and perhaps in other beings elsewhere, the universe has grown eyes and ears and minds. The hydrogen that formed in the first minutes, the carbon forged in a dying star, the oxygen released by ancient algae, have come together into a form that can look up at the night sky, trace the light back to its origins, and tell the story of its own birth. This is not a claim of human superiority, but of cosmic connection. We are not separate from the universe. We are its awake part. As you rest in the quiet dark, hold these three ideas together like a soft, three-stranded cord. The Copernican principle grounds us in humility and universal law. The anthropic fine-tuning fills us with awe at the precise calibration of our home. And Sagan's vision offers a purpose to our consciousness. We are the universe experiencing itself. Our science, our art, our quiet contemplation on nights like this, these are the cosmos becoming self-aware. We are transient, yes. Our planet is a speck, our civilization a blink. But through our collective curiosity, the universe that spawned us is able to comprehend its own vastness, its own history, its own beautiful, unfolding story. This brings our journey to a point of integration. We have traversed scale, probed darkness, witnessed the beginning, and pondered the future. We have listened to space-time rings and searched for other lights in the dark. Through it all, the narrative has been one of connection, of laws that bind the quantum to the cosmic, of history linking the first hydrogen to the neurons firing in your brain. We are not spectators of the universe. We are participants, made of star stuff, shaped by its forces, and gifted with the capacity to understand. And as this particular exploration draws toward its close, we find ourselves not at an end, but at a threshold. The mysteries we have outlined are not solved. They are beacons, calling us toward a future of deeper, quieter discovery. The greatest chapters of the cosmic story may still be unwritten, waiting for the next gaze upward, the next question whispered into the silence. Our journey has taken us from the infinite potential of the quantum foam to the vast, cold stretches of intergalactic space. We have traced the story of the cosmos from a silent singularity to a shimmering web of galaxies, and we have met its mysterious inhabitants, the dark, the dense, and the distant. Yet, as any good story reminds us, understanding begets wonder, and wonder begets new questions. As we draw this exploration to a close, we find ourselves not at a destination, but at a clearing in the forest of knowledge, surrounded by paths leading into even deeper, more beautiful mysteries. The cosmos, for all we have learned, remains a place of profound and gentle enigmas. Let us sit with a few of the greatest, not to solve them tonight, but to appreciate their quiet presence at the edge of our understanding. First, there is the dual mystery of the dark sector. What is dark matter? We have mapped its gravitational shadow across the universe. We know it sculpts galaxies and binds clusters, but we have never directly touched or seen a single particle of it. Is it a yet undiscovered elementary particle, a vast cloud of ancient, slow-moving entities that barely interact with our world? Or could it point to a subtle modification of the laws of gravity itself on cosmic scales? Similarly, what is dark energy? Is it truly Einstein's cosmological constant, an immutable property of the vacuum itself? Or is it a dynamic field that could change over time, perhaps even someday fading away or reversing its effect? These two dark components make up 95% of reality, and we know them only by their shadow and their push. They are the silent majority of existence, the greatest unsolved puzzle in fundamental physics. Then we peer into the ultimate abyss. What happens inside a black hole? Our equations point to a singularity, a point of infinite density where the laws of physics break down. But many physicists believe this is a sign that our theories are incomplete, that a theory of quantum gravity, perhaps string theory or loop quantum gravity, will someday describe the black hole's core not as a catastrophic end, but as a transition to something else. Does information that falls and truly vanish, violating quantum principles, or is it somehow preserved on the event horizon, encoded in two-dimensional holographic form? The black hole is a cosmic cipher, holding secrets about the marriage of the very large, gravity, and the very small, quantum mechanics. And perhaps the most profound question of all: was the Big Bang truly the beginning? What, if anything, came before it? Was it the ultimate beginning of time, or merely a phase transition from a prior state? A big bounce from a previous cosmos, or a bubble nucleating in an eternally inflating multiverse? Our physics runs out of road at the Planck epoch. The very concepts of before and cause may lose their meaning in that primordial quantum realm. The beginning whispers to us from the CMB, but its first faint story is one we cannot yet fully decipher. These are not failures of science, but its guiding stars. They remind us that curiosity is a perpetual flame. Each mystery is an invitation to look deeper, think more creatively, and build more sensitive instruments. The future of cosmology gleams with promise. Telescopes that will map the cosmic web in unprecedented detail, laboratories that might finally catch a dark matter particle, gravitational wave observatories that will listen to the hum of the universe's earliest moments, and perhaps, one day, a fundamental theory that weaves together quantum mechanics and gravity into a seamless tapestry. But beyond the specific questions, there is a deeper, more personal truth that this cosmic voyage affirms. To explore the universe is to explore our own origins. Every discovery in astrophysics is a chapter in our own autobiography. Learning how stars forged carbon is learning where our bodies came from. Measuring the expansion of the universe is measuring the history of the stage upon which we emerged. Contemplating the possibility of other life is contemplating the potential for kinship across the light years. We are not separate from this grand narrative. We are its most recent, conscious expression. So, as you slowly return from the depths of space and the beginning of time, carry back with you a sense of grounded wonder. You live on a planet that is both a tiny speck and a singular jewel. You are made of atoms forged in stellar fires, organized by laws tuned with exquisite precision. You are alive in a universe that is vast, ancient, mysterious, and yet in ways we are just beginning to understand knowable. The search for meaning is not separate from the search for cosmic facts. They are the same search. In seeking to understand the universe, we are seeking to understand our place within it. A place that is humble, connected, and astonishingly awake. The night sky is an eternal gift. It is a map of where we have been and a compass pointing toward what we have yet to learn. It invites us to keep looking up, to keep questioning, and to find, in its silent, star-dusted expanse, a profound and enduring peace. For in the end, we are the universe, contemplating itself. And that is a story with no end. And so, our journey through the cosmos gently ebbs, like a wave receding onto a quiet, dark shore. The grand images we have painted together, the swirling galaxies, the silent dark matter halos, the ancient whispering light of the CMB, begin to soften now, losing their sharp edges, blurring into a comforting velvety backdrop. Let them drift. There is no need to hold onto them. They have served their purpose, expanding your mind, stretching your sense of time and place, and in doing so, perhaps making the world within your walls feel just a little more peaceful, a little more spacious. Now, turn your awareness inward to the most immediate universe you will ever know, the quiet rhythm of your own breath. Feel the gentle rise and fall of your chest, a slow tide under a familiar sky. With each exhale, release any lingering thoughts, any final fragments of wonder about distant voids or stellar furnaces. Let them go. They are safe. The universe will keep them, tend to them, and unfold its stories with or without our watchful gaze. It has done so for billions of years, and it will continue with a patience that cradles all our hurries and worries into insignificance. Feel the weight of your body surrendering to the surface that supports you. Notice the subtle textures around you, the softness of fabric, the firmness of the mattress, the still air of the room. This is your own local space, your own private corner of the cosmos. Here, the forces are just right for rest. The gravity that holds you is gentle and familiar. The silence is a gift. You are, in this moment, a perfectly situated world at peace. As your eyelids grow heavy, imagine not the infinite void, but the infinite embrace. You are not a speck lost in the dark. You are a node in a magnificent, living web of existence, connected by stardust and story to everything that has ever been. The same atoms that now compose your resting form have danced in cosmic winds and witnessed the birth of suns. You are not separate from the universe. You are of it. And in this profound belonging, there is a deep and abiding safety. The cosmos is not out there. It is in here, in your breath, in your quiet, slowing heart. Let the last conscious thought be a simple sensation. The feeling of drifting, not through space, but through a deep, warm, and silent ocean of peace. The questions are put to bed. The mysteries are allowed to simply be. There is only this breath, and the next, and the soft, welcoming dark behind your eyes. Let go into it completely, trusting that you and all things are held in the graceful, unfolding story of a universe that is, above all, a place of wonder and rest. Good night.